This problem has us find the response of a mass that is subjected to a ramp function that then flattens out to a constant value force. We're giving some information here. I'll just put it right on the plot that the T0 is 1.5 seconds, that the ramp is going to last before it's flat, and then it's going to level off to a value of 100 newtons at that 1.5 seconds, and it linearly increases between 0 and the 1.5 seconds. So we're going to do this first as an undamped system, leaving C as 0. Then we'll do it again, and we'll add a value of C to just see if we add a little bit of damping, what is the response going to look like then. So we want to find the full response, we'll call x of t when we get our model. So originally, no damper, we just have our spring. X of t is going to be our vertical deflection. We are provide the mass and the spring constant right away, so the modeling step will be, as far as those parameters, pretty straightforward. We will use m is 10 kilograms, k is 5,000 newtons per meter. I'll go right into base units, and a c of 0. And we'll modify that for the second part. So that's our MRC, our K. This is a forced system. It has some f of t being exerted on it. So our f of t, we want to create, we're given it graphically, we want to create a functional definition of this f of t. So if we look at our plot, it's this linearly increasing ramp from 0 to 1.5 seconds, and then it's flat. So we could write it as 100 over 1.5 times t from 0 to the 1.5 seconds. And that's going to simplify to 67 with some rounding, but I'll do that later. And then on the, we'll have a second interval after 1.5 seconds. It has a different definition. So one way we could define it is simply, we could say, oh, okay, it's 100 at 1.5 seconds, and then it goes on. And that is a perfectly fine way to define this piecewise function for f of t. If we want to treat this in the way we treated our general forcing in the first subsection, we could do a Fourier series expansion on this f of t, we could get an infinite series, and we can get the exact solution that way. And that's a good way to do the problem. We're going to have an infinite series though, so that's just going to be a little bit of a pain. So we're going to do this one a little bit differently. I'm not going to just say, it still has to be 100. This still must be true, but I'm going to write the 100 in a different way so that we can treat this as an aggregate force profile. So the first part is okay, but I need this in the form of f of t is going to be some f1 of t on the first interval, and then it's that f1 of t plus an f2 of t minus t1. I guess I'll do it this way. So I have to keep adding forces together in order to use that aggregate force profile, and they all have to be forces that are, at least for the purposes of this course, each one is a ramp, an impulse, or a step function. So when we're on this second interval, this will go till t1 is the general form. And from t1 greater t, this one, it just keeps going. This is the way we need to write our force profile. So we have to copy everything from the first row into the second, then add another force. And if we had a third interval, we don't in this one, but in a third interval, we would copy the entire second row into a third row. So right now it doesn't look like that format. So I'll get rid of this and we can rewrite it. It still has to be 100, so we'll see what that looks like. But I have to start with everything from the row above it. And at this point, I'll just rewrite this as the 67. So it's a little bit more compact here. So it's obviously not 67t, but we have to get it so that 67t plus f of t minus t1 is equal to 100. The result still has to equal 100. We're just writing it in a very specific way so that we can solve this using the aggregate force profile. So we have to figure out what that f of t minus t1 is going to be equal to. And specifically here, we know the t1 is 1.5 because that's the end of that first interval. So we might be tempted to say, okay, well, this is a profile of we have a ramp function and then we have this step function, because a step function looks like that flat 100. But that's not the case here because we're not adding a step function to the ramp function. So keep in mind, what is f of t in this piecewise is we are able to turn on a function, but we're not able to turn off a function. So we need the aggregate of one function plus another. So really what's happening here is that the first function is this. It just keeps going up. That's the 67t. But at that 1.5 seconds, the actual function becomes flat. So what we need is to undo this first function that just keeps going up and up by basically we can subtract that part of it and then add 100 to it. So what we can do is come in with our second function looking like, well, it doesn't turn on until here. If we add these two functions together, the result is going to be the 100 Newton force. So we already have this ramp function going up. We need actually a ramp function coming down so that the sum of these two ramps is 100 newtons. So what we can do is we can say it's 67t plus, really minus, because it has a negative slope of this ramp, minus 67t minus 1.5 equals 100. Well, we can check this. So this is 67t minus 67t plus 100 when we round off a little bit. Those are going to cancel. So we get 100 equals 100. So the result is still 100. However, I'm going to write it in this specific way. Okay, so the tricky thing on this one is that really we are adding a positive ramp. We start it, and then to kind of undo it at 1.5 seconds, we have to add a negative ramp that's going to cancel out that otherwise increasing force. So again, the piecewise function I'm still writing as 67 times t for the first 1.5 seconds, and it is still 100 after 1.5 seconds, but it's in the form of this f1, and then the second row is f1 plus, so this is the f1 plus f2 t minus t1. So now it matches the form we want for our aggregate force profile. So the aggregate force profile for this one actually does not have a step function. It has a ramp, and then to that ramp, we're going to add another ramp function. And again, I want to re-emphasize, we could have left it as 67t on the first interval and 100 on the second, and solved it using Fourier series expansion, but we couldn't write it exactly that way and use the aggregate force profile that we're going to proceed for the solution in this example. So that is why I'm writing it in this very specific way for the f of t. At this point, I can write the equation of motion is going to be, well, I just have a spring mass damper. I will write the generic form with the c because I will add that when we analyze this kind of a second time. And I'll just leave the right-hand side f of t. So for this first way we analyze it, we are going to have 10x double dot plus, I'll leave that c out now that it's 0 for this specific first case, equals our f of t. All right, so we can identify the system. We have 1 degree of freedom. In part A, it is undamped, which actually won't really matter for how we're going to be solving this, as we'll see in a second here. We are going to be linear, we are forced, and if we see, again, the way we wrote our f of t, this is general forcing, but specifically we're going to, so I will say general forcing, because of the way the right-hand side is this piecewise function. It's not a simple harmonic, but our solution strategy will look different than if compared to how it would look if we used a Fourier series expansion. So this is why it's going to look different here, because we are writing our equation in this form of f of t. So we have this f1 of t, that's the first ramp, and then the second row is that same ramp that carries through, plus that negative ramp that cancels it out so that the sum of these two terms is 100. And we only have 2 rows in this one. So we wrote in this specific manner so that our solution is going to look like this x of t. That our solution is going to be a piecewise function. So we have our x1 of t. That's going to carry through. So that's our solution to f1 of t. And in this case, it's a ramp. And then on the second piece of this, on the second interval, that first solution keeps going, and we add to that the solution to f2, which is going to be the solution from that negative ramp. So our solutions are both going to look in this form. This is our solution because we have these 2 ramps. However, they're going to have different amplitudes, although they're going to end up being equal and opposite. So this is the solution we're going to be applying in our aggregate form. So our x of t is going to very generically right now be x1 of t from 0 to 1.5 seconds. And it'll be x1 of t plus x2 of t minus 1.5 for, in this case, anything after 1.5 seconds. So notice also the forcing we have, just to reemphasize why we're doing it in this manner. It's non-periodic, it's aperiodic. It ramps up and then it's just flat. We don't have a repeating pattern like we did in a lot of the other examples that we encountered. So this is a good application of the aggregate force profile. Now again, even for non-repeating or aperiodic functions, we could do a Fourier series expansion, but it gets a little tricky because how do we define the period of repeating pattern because it doesn't repeat itself? So we could draw it out and say, well, it's, let's just say 100 seconds or something and do it that way. And that would work, and our solution would be good for only 100 seconds though, because with the Fourier series expansion, we're presuming it then repeats itself starting at 100 seconds. It would drop back down to 0 and then go up. So Fourier series would work on this. It's not the most convenient though, being an aperiodic function, and we can get a more compact closed form solution using the aggregate force profile. So it's going to look like this piecewise function here. The x1 of t we need to solve for, and the x1 and the x2 of t we need to solve for as well. And we'll do that because we know that our x1 of t, actually the x2, I'll just write the x1 of t1 here so we can see what it looks like, is going to have this general form of the force over k times t minus 2 zeta omega n plus e to the negative zeta omega nt times 2 zeta over omega n cosine omega d times t minus omega d squared minus zeta squared omega n squared over omega n squared omega d sine omega dt. So a lot in here, but some of this is going to drop out, and actually we're going to see that the f values are equal and opposite. So really we just have to solve for this one time. But we can start putting together some of our parameters and then put together our total solution in our assemble step. 1 degree of freedom, we will find our natural frequency first, k over m. And this will be the same for the damped or the undamped system. The natural frequency is going to be in this one. We have a k of 5,000 and an m of 10. And these are in base units. So our natural frequency is going to be 22.4 radians per second. Our zeta is c over 2m omega n. At least for this first part, zeta is 0. This is undamped, which means our omega d is going to be, in the part A at least, the same as our natural frequency, 22.4 radians per second. And this lets us go on to our assemble step. So let's put together our x1 of t. All right, so it's this f over k. F is the force per second when we are using the ramp force aggregate profile. So if we look up our definition, 67 is actually the f value for this problem, not 100. It's the 67 because that's what's being multiplied by t in our piecewise function. So we'll have 67 over k, which was 5,000, t minus, now we have, at least in part A, 2 zeta over omega n. Well, it's always that, but zeta is 0 in this first version of it, so that's not going to be present at all. So that term is going to go away, at least for part A. Plus, we have e to the negative zeta omega nt. Again, zeta is 0, so e to the 0 is just 1. So this is going to be just t plus 1 times 2 zeta over omega n. That's just going to be 0, so that goes away. I'll be left with negative omega d is 22.4 squared minus zeta omega n. Zeta is 0, so that goes away, over omega n squared omega d. For part A, omega n and omega d are the same, so that's 22.4 to the third power sine of 22.4 times t. And this will actually simplify down. I can do some cancellation here, and we get this. And I can get rid of some of these parentheses, close this in just a little bit then. All right, so for this first one, the undamped one, a decent number of terms dropped out, so that was favorable to us. And this is what we get for our x1 of t. This is the solution to just the first interval where we have f1, that ramp function of 67t acting by itself. Now we need our solution for x2. If we go back up to how f of t is defined, now we have this second piece here. It's in the form that we want. It's a ramp again, but it has that amplitude of negative 67 newtons per second. Now, again, it's written with this offset, which is good. This t minus 1.5, that's exactly what we want. This is completely in the right form for what we're looking for. So it's going to turn out that it has the negative amplitude that x1 did. This is just negative x1 of t, because everything else about this is the same, except the 67 is actually a negative 67. So I don't need to rewrite this whole thing. But now when I put together my total solution, my x of t is going to be just my first solution, x1 of t, and that is good for t up to 1.5 seconds. I'll use a less than or equal to. Again, it really doesn't matter. Then in that general form, I copy my x1 of t plus x2 of t minus the 1.5, and that's going to be good for the rest of time. So this, very compactly written, but we can see above what it really looks like. This is actually the closed form solution for this problem. Pretty tidy. We didn't have to do an infinite series to get this. And because there's no damping, a lot of the terms dropped out here. But again, we have formed our total solution, our complete analytic solution, using this piecewise definition, that we had to split our forcing function into these intervals where we could describe it using the simple forces like a ramp, in this case a ramp and then another ramp, or if we had a step like we'll do in subsequent problems, or if we had an impulse like we'll do later. That's what we want to break the f1 and f2 into, and then we can get solutions for this x1 and x2. So next we're going to see how we can plot this in MATLAB and see visually what our total solution looks like. This is the closed form solution. Now we want to plot it. Now, plotting this piecewise function just gets a little bit tricky in MATLAB, so I'll show you how I went about doing it. So first I'm putting in all of my parameters here and getting all of my properties out, making sure that everything agrees. And yes, we get the same natural frequency, the 22.4. For right now, zeta is 0, and our damped frequency also 22.4. And I'm going to show how I plot this function to just make sure it's plotting correctly. So I'm going to make my forcing function f this inline function of t. So we can do piecewise functions in MATLAB using logical comparisons. So this is being written just like it was on the by hand, where I have my f1 of t. That's this ramp up, where it's going to be this 100 over 1.5. That's what I rounded to 67 times t. So that is always on for t greater than 0. And then we turn on f2, which was this function, this negative 67 times t minus 1.5. That's what this is doing. And that only turns on, though, once we hit that second interval of 1.5 seconds. That's what this logical comparison is doing. This is sometimes called a comb function, because what is it going to do? Well, it's going to take a value, since it's just a logical comparison, when this is not true. That is to say, in this example, any t less than 1.5, this will evaluate to 0. And then I'm going to multiply that 0 by my second function, and that will automatically be 0. However, any time where this is true, let's say 1.6 seconds, that will evaluate to true, or 1, and that 1 gets multiplied by this second function, which effectively will turn it on. So if you see what's happening here in the next line, I'm going to do this over 5 seconds. I'm defining a bunch of t values from 0 to 5, and then when I call my function, all those t's less than or equal to 1.5, this second part will be completely gone. But for any t where it's greater than 1.5, it's going to add the first part, and now the comb function will turn on, and it will add that second part. So this is a way we can make piecewise functions in MATLAB using this logical comparison, the comb. And we'll do this for more complicated functions in the next examples as well. So let's see what happens. Just make sure this works when I plot up to here. I just want to plot the function, make sure it looks the way I think it does. And yes, I get back that original function. So again, with just one definition of the function, you could also do this with if statements. I think this works a little bit cleaner just with one inline function here. For the 1.5 seconds, we see that it is ramping up. And then after the 1.5 seconds, it is just this steady 100 Newton value. So we've recovered that original function that we were given graphically because we wrote it as a piecewise function, and now I put that piecewise function into MATLAB. Now I'm ready to define my responses, my x's, my x1 and my x2. So I have them here just generically because we're going to go through this again, and I'll put in some damping so we can just see what happens. So this is exactly the definition that was on the slide for the solution when we have a ramp input. So I have here this f I've defined is that 100 over 1.5, that about 67. So the f over k times all of this business. So I'm defining each part of my piecewise solution. I have my x1 defined. And I define my x2. So instead of I could just rewrite the whole thing, but with a negative f, but we already said that x2 is just a negative ramp of x1. So I don't need to rewrite that whole thing. I'll just define it as negative x1. And then we can see how I assemble the piecewise function solution. So in a similar idea of how I define the forcing, that x1 is always on for all positive values of t, or all t greater 0 or greater. And then the second part of the piecewise function is going to come again with this comb, this logical comparison. So I don't want this to be on for times less than 1.5, and it won't be because the logical comparison will be 0, and it will zero out this second part of the solution. But anytime the t is greater than 1.5, that logical comparison will be 1, and then it will include this part of the piecewise function. So this big X of t is that total solution. This is the entire piecewise function put together on the first interval, which is the x1 of t, and then on the second interval, where it's the whole thing, it's the x1 of t plus the x2 of t minus 1.5. And then I'm going to plot it. So certainly the tricky part about this one is, in MATLAB at least, putting in those piecewise functions so that it is correctly interpreting them. So I had a piecewise at the definition of my forcing. I really didn't need that for this problem because I came up with an analytic solution just on paper. But to plot it, we can see how that works. And for the solution, the total x of t, I also am using this piecewise function with the comb function. So I'm going to plot this big X of t. That is my solution. All right, so this is what it looks like. So as the force is increasing, we're seeing this ramping up. We're seeing the response has some oscillations in it. And then we have that constant force after the 1.5 seconds. And we see, okay, our mass keeps oscillating up and down between these two extreme values. Again, we have the analytic solution to this, but graphically it's going to have a lot more meaning for us to look at. Make it a little bit bigger for us. All right, and remember, this one had no damping in it, so those oscillations do just continue on forever once we are forcing it with that constant 100 Newton force. So for the most part, the behavior of the system, it has some more oscillations in it, but more or less it looks like the forcing function. Certainly with different amplitude though, it ramps up and then it is at least steady around some constant around 20 millimeters here as time goes forwards. So this is the response of this casting when we ramp it up with the sandblasting and then we hold it at a constant 100 newtons. It's going to oscillate between, get a rough idea here, about 21 and 19 millimeters and keep going if we have no damping in the system. So let's put in some damping and I'll let Mathematica do the work for us here a little bit. Instead of 0, let's put in a little bit of damping. Let's just say put in 25 Newton seconds per meter. Now, a nice thing about using MATLAB is it's going to calculate the zeta for us. It's going to redefine our x1 and our x2 automatically. So actually, I've already set this up to work for any m, c, and k that we put in here. So now, answering the second part of that original question, what if we have a little bit of damping? What's this going to look like? All right, so resolving everything, we now have a damping ratio of, we see about 0.06. So we have a little bit of damping here, but definitely the response is different now when there's damping in the system. We still have this ramping up. We still have oscillations here. We get to around that 1.5 seconds where we have a constant 100 Newton force. But now we see that those oscillations, due to that constant force, eventually are going to die out because there's dissipation in the system once we add even that minor damping of 25 Newton seconds per meter. So at steady state, we're at 20 millimeters is the constant value of displacement of the mass. So going back to our solution, the modeling part, at least the MCK, was just given to us, so that was easy. The f of t, for this problem, we could have written as 67t on the first interval, 100 on the second. However, we want to write it in the specific form to be able to use the aggregate force profile, is why I rewrote that second line. If we work out the algebra, it is exactly equal to 100, but written in a form of one function plus another function, specifically a ramp up plus a ramp down. So what that let us do is in our identify step, we saw, okay, we are going to then use our solution will also look like a piecewise function where we're going to keep copying the solution above and superimpose on it the next solution. So x1 was the solution to our f1 force, x2 was the solution to our f2 force. These were both ramps, so x1 and x2 had that same form that we got from our slides. And then we just had to figure out our parameters and assemble our entire solution. And we saw we got this piecewise function of x1 is defined and x2 is defined, although in this case x2 was negative x1 because they had that same forcing amplitude, that 67 newtons per second.